In Chapter 15, Section 7, we'll look at cylindrical triple integrals, and we'll see how this can greatly simplify things when we are dealing with curved surface, curved volumes, things that have symmetry, that are being rotated about an axis, stuff like that. Okay, so the first problem says find the rectangular coordinates of the point whose cylindrical coordinates are given. So when we have cylindrical coordinates, they're giving us r, theta, and z. And what we're going to try to do is write that as x, y, and z. And we're going to use the fact that x equals r cosine theta and y equals r sine theta and z equals z. Okay, so in this problem they tell us we have 4 pi and e. So therefore x is going to be r, which is 4, times cosine of theta, which is pi in this case. But cosine of pi is -1, so our x value is -4. Y would be equal to the radius 4 times the sine of theta, which is pi. And sine of pi is 0, so we just get 0. And then z in this case would just be equal to e. So our point is going to be -4 in the x, 0 in the y, e in the z. And that's what we have here. Okay, then they give us a point 0, -3, 3, which is r, theta, and z. And I'm missing something here. It's, oh, I was looking at the wrong thing. So it was 3 pi over 2, and 3. Okay, so x is going to be the radius, which is 3, times the cosine of the theta, which is 3 pi over 2, or 270 degrees. And at 270 degrees, the x value is 0. Then y is going to be 3 sine of 270 degrees, or 3 pi over 2. And sine of 270 degrees is -1, so we get -3, and e is equal to e. Z is equal to the third coordinate, which they said was 3, so it's 3 for us as well. So our point is 0, -3, 3. So problem 1 should be quick and easy. Okay, problem 2 says, describe in words the surface whose equation is given. Theta equals pi over 4. Well, theta equaling pi over 4, if we think back to unit circle, let me actually see if I can draw this. So theta is measured from the x-axis and goes counterclockwise. So theta is 45 degrees, pi over 4. And that creates a line that goes out like this. Well, this line actually creates a plane. It actually goes this way too. And so it's going to go up and down for infinity. So it's a plane that looks like this. And at 45 degrees, the x and y value are exactly the same. So y equals x is the plane where x and y are not negative. So if x and y are not negative, then we're only going to have this portion of the plane. So it's going to go up along the z-axis and forward like this. Okay, so that would be the plane. Also, hopefully not too bad. Okay, problem 3, they want us to go from cylindrical, from rectangular coordinates to cylindrical coordinates. So we have in part A, 7x plus 6y plus z equals 2. And basically we're going to solve for z. So we're going to say z is equal to 2 minus 7x plus 6y. And then we're going to recall that x is r cosine theta and y is r sine theta. And the only thing that we did is we factor, oops, I missed a minus sign here. So if I pull 6y over here, it's not going to be plus anymore. It's going to be negative. And then we have a negative r, so the last thing we can do is factor out a minus r, which leaves 7 cosine theta plus 6 sine theta. Yep, that looks the same. So that's correct. In part B, we're going to say we have minus 5x squared minus 5y squared plus z squared equals 6. Well, again, we're going to solve for z. So we're going to have 6 plus 5x squared plus 5y squared when we move those over. Or we're going to get z squared is equal to 6 plus 5 x squared plus y squared. And we're going to have z squared equals 6 plus 5 r squared. So all of this is just r squared, and we can just write it like that. Z squared equals 6 plus 5r squared. Okay, so that's problem 3. Also, hopefully not too bad. 4, also not too bad. No arithmetic for us to do. We just have to look at what are the limits of the integration and what volume would that carve out. So we have r goes from 0 to 5. Now, if we had r going from 0 to 5, that would create a circular cylinder. Actually, you could create this circular cylinder right here. So I have to draw this. So we would start with this circular cylinder that has radius of 5, so it's going to go to minus 5 and positive 5, and then it's just going to go up along the z-axis. So let me not try to butcher this. They've already got a picture for us. Okay, so far that's right. But let's see what's going to be restricted. Then it says theta goes from negative pi over 2 to pi over 2. That's actually going to cut this thing in half. And it's going to cut it in half through the x-axis. So it's going to cut this cylinder in half, and this back half is going to be gone. So now we're down to this picture. So this is half of that cylinder they drew down below. Then the z goes from 0 to 1. So z goes from 0 to 1. It's going to chop this cylinder off so it doesn't go any higher than that. Okay, so by process of elimination, we can pick the correct picture is this top left picture. Okay, based on the last couple sections where we've done conversions to polar coordinates, cylindrical coordinates are very similar. It's pretty much the same thing. We're going to start to immediately make some shortcuts. So we're going to call this right away square root of r squared. And we're going to say, oh, this is r squared equal to 4, which means r is going to go from 0 to 2. And then z is still going to be z, so we have to still use that. So we're going to say, oh, square root of r squared is just r. So right away, we're going to start to change this limits. Instead of square root of x squared plus y squared, we know that that's just r. And since this thing is a full cylinder, we know that theta goes from 0 to 2 pi. And we also know that theta is now the last variable. And we know r, in this case, goes from 0 to 4. So we know dr is the second variable, moving outside to in. And then we know z goes from minus 3 to 4. So z is the second variable, is the first variable. But we have to add an r dr, so there's actually another r that comes out of this. Okay, but when we take the antiderivative of this, the first letter is z, so there is no variable. So we're going to get 0 to 2 pi, 0 to 4 of z r squared from minus 3 to 4. dr d theta. This is going to be 0 to 2 pi, 0 to 4. This is going to be r squared times 4 minus 3 dr d theta. 4 minus 3 is 7, and it's a constant, so it's just going to come out of the integral. 0 to 2 pi, 0 to 4 of r squared dr d theta. Antiderivative of r squared would be r 3 over 3 from 0 to 4 d theta. This is going to be 7. This will be 4 cubed over 3 minus 0 cubed over 3 d theta. 4 cubed over 3 is just another constant, and it's going to end up being, let's see here, 4 cubed, you're going to get 4 cubed times 7 over 3, which turns out to be 448 over 3 times the antiderivative 0 to 2 pi d theta, which is 448 over 3 times 2 pi minus 0. And we're going to get 896 pi on top over 3. So it's not bad if we immediately kind of jump to our cylindrical coordinates and get rid of these square roots and get rid of these x squared plus y squares, change them to r's and thetas and z's, and it's not too bad. Okay, very similarly, I'm going to immediately start to change stuff. So it says z is bound by the cone square root of basically r squared. But it's also bound by 162 minus, in essence, this is also r squared. So imagine we're subtracting r squared over, and to get rid of this 2, we take a square root. Okay, so our integral is going to be, again, we're going to go from 0 to 2 pi because it's a cone, and a cone will have a full rotation, 360 degrees. Now, r in this case is going to go from, okay, so if we can have r squared going from, okay, to find the bounds on r, it's a little trickier. So from this one it says z equal r. And from this one it says z, actually let's write it a little differently. Let's write this one. This says r squared plus z squared has to equal 162, where these two surfaces meet. But we're going to replace z with r. So this really says r squared plus z squared, which is r squared, equals 162. Well, that would be 2r squareds equals 162, or 1r squared equals 81, or 1r equals 9. So r is going to vary from 0 to 9, and then z is going to vary from r to this square root of 162 minus r squared. And the limits of integration would be dz r dr d theta. But when we take the antiderivative of this z, there is no z's in here, so we're just going to get 0 to 2 pi, 0 to 9 of the square root of 162 minus r squared minus r, all times r, and then dr d theta. So we're going to get 0 to 2 pi, 0 to 9 of r times the square root of 162 minus r squared dr minus, I'm going to break this into two integrals, 0 to 2 pi, 0 to 9 of r squared dr d theta. The reason I did that is because we have to use u substitution on this one, but we don't have to use it on this one. So we're going to let u equal 162 minus r squared. Therefore, u of 0 will equal, let's see here, u of 0 will equal 162, will be 162, and u of 9 will be 162 minus 81, which is 81. And we're going to get du equals negative 2r dr, or dr equals du over negative 2r. So the first integral is going to become r square root of u dr, which is du over minus 2r, and then it's d theta. Now the second one, we can actually perform this antiderivative. This would be r3 over 3 from 0 to 9, then the d theta. Okay, let me get rid of some of this that we already did. Okay, now this one, this r cancels with this r. We get 1 over minus 2, which I'm going to pull out. So we get minus 1 over 2, 0 to 2 pi. Oh, I forgot something here. This would still have the antiderivative from 0 to 9 of r. Actually, no. It would be 162 to 81 of u. So we change those limits. So this is going to be antiderivative of 162 to 81 of u to the 1/2 du, d theta, minus, let's perform this one, 2 pi. This would be 9 cubed over 3 minus 0. This one's going to be minus 1/2, 0 to 2 pi. Antiderivative of u to the 1/2 is u to the 3/2 over 3/2 from 162 to 81 d theta minus, this is going to be 0 to 2 pi of 243 d theta. Okay, this is going to equal minus 1/2. We're going to get, let's see here, this is really 2/3, so it's 2/3. And we're going to get 81 to the 3/2 minus 162 to the 3/2 d theta minus 243, 0 to 2 pi d theta. This is going to be minus 1/3. So I'm going to cancel this 2 and this 2, and then 1 and the 3, 0 to 2 pi. This is going to be 729, 81 to the 3/2, minus 162 to the 3/2 is 1458 square root 2. And then we can have d theta minus 243, 0 to 2 pi d theta. So we're going to get minus 1/3, 729 times 2 pi. I'm skipping one step here in that these are just constants. So the antiderivative is just going to put a theta in front of each. The theta is really just 2 pi because 2 pi and 0, the 2 pi will stick around, the 0 will go away. So it's really minus 1458 root 2 times another 2 pi. And then from this one we get, so that's the end of the minus 1/3. Then we get minus 243 times 2 pi. And if you do this 729 times 2 times 1/3 is going to be minus the 243.2 pi is going to be minus 972 pi. So this term will come from this applied to this added to this, and then so that's that term, and then this term is just minus 1/3 times minus 1458 root 2 pi. That will give you this. Okay, so it just gets a little messy because of the numbers here and the fractional powers, but if you do it, you will get those values, and that's problem 6. Okay, in problem 7, again, we're going to kind of immediately start to shortcut the problem. So we have from minus 4 to 4, then we have minus root 16 minus y squared to positive root 16 minus y squared. And then we have square root of x squared plus y squared all the way to 6. And they have xz, dz, dx, dy. Well, this is a cone, and a cone is going to have 360 degrees, so 0 to 2 pi for theta. We've seen this many times now. When you have 16 minus y squared, we can set up the equation where these are x's now because of this middle term. So this is like saying x equals this. Let's just write it. Then you square both sides, and you add y squared to both sides. Well, x squared plus y squared is r squared. So r is going to go from 0 to 4. And then the last one, square root of x squared plus y squared is, so this is equal to the square root of r squared, which is r. So this is going to go from r to 6. Now x is actually r cosine theta. So we change that x to r cosine theta. Z is just z, so we're going to keep z like that, and then we're going from dz, now we're going to r dr d theta. And we have the antiderivative of z is z squared over 2 from r to 6, and then we have, I forget, r cosine theta. Then we have times another r dr d theta. And we're going to factor out the 1/2. And we're going to have, let's see here, 0 to 4. Z squared, which we're replacing with 6, so it's 36, minus the lower limit of r, which is r squared. And then we have another r squared cosine theta dr d theta. But we're going to have to distribute this. Of 36r squared minus r to the 4th. And yeah, and then we have cosine theta, dr d theta. But when we're dealing with r, cosine theta is just a constant, so we're going to have 0 to 2 pi times the quantity 36r3 over 3 minus r5 over 5. That's going from 0 to 4. Then we have times cosine theta d theta. And so we're going to get 1/2, 0 to 2 pi, 12 times r, which is 4 cubed, minus 4 to the 5th over 5. Then we have cosine theta d theta. And we're going to get 12 times 4 raised to the third is 768. 4 to the 5th over 5 is, well, basically when you combine these two terms, you're going to get 2816 over 5. And then we have the antiderivative from 0 to 2 pi of cosine theta d theta. This is 2816 over 10. Antiderivative of cosine is sine from 0 to 2 pi. This is 2816 over 5 sine of 2 pi minus sine of 0. But sine of 2 pi is 0, sine of 0 is 0. So this is equal to 2816 over 5 times 0, which is 0. So the whole thing reduces to just 0. And that's problem 7. Okay, problem 8, they actually set up the integral for us, including having it in cylindrical coordinates. So this one's not too bad. We just have to plug in the numbers and perform the arithmetic. Oops, not CR. And be careful, they have d theta in the middle now. We've usually had it at the end. They start with z like we have been doing, but they've left r for the end. So we're going to get the antiderivative of this, since there is no z, we're just going to add a z. And z is going to go from 4r to 24. Then we have the d theta dr. So we're going to get 0 to 6, 0 to 2 pi. This is going to be r times 24 minus 4r d theta dr. This will be 0 to 6, 0 to 2 pi of 24r minus 4r squared. But again, r is just a constant in this context, so it's 0 to 6 times the quantity 24r minus 4r squared times theta, the antiderivative of d theta, and that goes from 0 to 2 pi. Then the r. So this is just going to be like multiplying by 2 pi because the 0 doesn't do anything, and the 2 pi I can pull out. So it's 2 pi, 0 to 6 of what we had before, 24r minus 4r squared, dr. This is 2 pi times the quantity, 24r squared over 2, minus 4r3 over 3, from 0 to 6. So we get 2 pi, 12 times 6 squared, minus 4/3 times 6 to the third, minus 0 minus 0. And if you do all this, you should get 288 with that pi. So not too bad there. They gave us the setup, and we just had to perform the actual integration. Problem 8. Okay, problem 9 is a true or false question. The integral below represents the moment of inertia about the z-axis of a solid E with constant density K. So we have some E, and basically we have K times R squared times R dz dr d theta. So this is our density function. Okay, and moment of inertia is equal to, about the z-axis would be, in the z direction would be mxy, which is z times the mass function. But the mass function is, this m, the mass function is the triple integral of the density function across that volume. So the triple integral of this k, which we're calling the density function, would be the mass. And then timesing it by z, so let's see here. So this triple integral and that k across r dz dr d theta is all going to be the mass function. And then times z would be the only other thing we have to pick up. And so z in this context is going to be r squared. So this is like the underlying portion is the mass function, and then the only thing left over, the r squared, in this case is the z function. And so we multiply these two together, that would give us the moment of inertia. So this setup is true. So that looks good for problem 9. Okay, problem 10. They say the integral below represents the volume enclosed by the cone, z equals, so once again we kind of saw this, square root of r squared, which is r, and z equal 4. So this goes from r to 4 in the z. R to 4 in the z. Correct. Which means that when these are equal, the radius would have to go from 0 to 4. That's also correct. And if it's a cone, it's going to be a full 360 degrees, so 0 to 2 pi is correct. This is very close. The only thing that is incorrect is what? They forgot the limits of integration are r dr d theta. There's a missing r right there. So that's the only reason that that is false. Okay, so that will complete problem 10 and section 15.7.